All right, here we go. Lesson number 3. Lesson is in 2 parts. So we're going to talk about the first couple of these essential learnings in the first part of this lesson, and then we're going to talk about the second 2 in the next part. So first of all, acceleration looks at the change in velocity over time. Okay, so just like velocity looked at the change in displacement or the change in position over time, acceleration describes change in velocity over time. Second thing that we're going to talk about is that we begin our investigation by looking at position time graphs. And for any object that's accelerating, we get a curve. Okay, so these are not going to be straight lines, these are going to be curves, which make our analysis a little bit trickier. Last but not least is this bullet point for today. We're going to talk about instantaneous velocity. For any object, the instantaneous velocity is the velocity at some instant in time that we're referring to. And we're going to come back to that, and we're going to see in this run through how to find an instantaneous velocity. Okay, so as we saw before, when we're talking about position time graphs for anything that's accelerating, we get a curve. And so here is an example of a position time graph for a train, and you can see that it starts at a displacement of 0 and ends up at a displacement of 250 meters east. And when we read this graph, we find a piece of information. First of all, that anything taken, just like in our previous lesson, instantaneous values of position is what we get when we read values off of this graph. So for example, we might say then at t equals 4.5 seconds, and we could look down here, use our ruler, and we could estimate that at t equals 4.5 seconds, we get a displacement of approximately, yep, you can read it right off the graph, 125 meters east. The train has a position of 125 meters east. Again, it's a position time graph, so don't forget the direction. Okay, fair enough. That's a review of yesterday, same thing as yesterday. However, now we come to something that's a little bit different. We come to this, okay, finding a slope. And so the first thing that we want to say is, well, to begin, how do you find the slope of a curve? And of course, what we're going to say and what we're going to talk about is we're going to look at this in pieces. So if we look at the beginning of this graph, we're going to zoom right in, very beginning of the graph. And if I was to say right here, is this kind of a straight line, this little segment right here? Yeah, this is a straight line. So if I found the slope here of this little part of the graph, I could say, okay, well, that would be one value. But then if I go a little bit later on in time, let's say I go to 4 seconds, and I say, okay, well, I could approximate this. You know, I could find maybe the slope of the curve right here, okay? But then when you look at these two values, this slope, this first one down here, is not as big as this slope up here. And then we come to the end, and it's like, oh, holy cow, look at this. I could do this one as well. What is happening to the slope of this line is that it is increasing as we go along. Okay, so that's a note that we want to make. The slope of the curve is increasing. Okay, and this is important because when we talk about the slope on any position time graph, this is telling us something. This tells us that the velocity is increasing. Okay, and the reason that we know this is because, like we learned yesterday, one of our essential learnings, slope and velocity when it comes to position time graphs are the same thing. Okay, so one means the other. So the question then becomes, okay, how do we then determine a velocity from this graph? And the way that we're going to do that is we're going to set up a definition. Okay, so we're going to set up a definition, and we're going to do it right here with the room that we have. So the instantaneous velocity of an object which is the velocity at some instant in time can be found by determining the slope of a tangent line drawn at that instant. All right, so we have to talk about what a tangent line is, but this is what we're going to do. So we've got that if we want to find the instantaneous velocity at some instant in time, let's say we want to find the instantaneous velocity at 3 seconds, then what we do is we need to draw a tangent line to our curve at 3 seconds, which is what we're about to do now. So here we are, we're going to zoom in on this curve. I'm going to get rid of these little red arrows because I don't want to confuse the fact. We're going to come right back to drawing a tangent. So you need a ruler in order to do this because tangent lines have to be lines. And a tangent is a line that touches the curve at only one spot. So some of this, especially when we do it by hand, is going to be a little bit of eyeballing. So I've got my ruler and I'm going to lay it down here and I'm going to try and get a fairly decent tangent line. And that is not terrible, but this is not, it's also not that great. So if I want to correct this, then I would need to rotate this a little bit. And you can see that if I was to do this, this might be a little bit better. There, that's a little bit better. Again, drawing this, now when you zoom out, that's actually not too bad at all, okay? So the thing is that drawing tangent lines is a little bit tricky. You know, it takes a little bit of eyeballing. But now, this is the thing, now that I've got my tangent line, I can find the velocity of this train at 3 seconds because I've drawn a tangent line there. So if I now find the slope of that tangent line, and so this is what we're going to call it. We're going to say V3, which is the slope of the tangent line at 3 seconds, okay, is equal to, and we're going to do this in the same way as we did before, D2 minus D1 over T2 minus T1. And so I can come to my tangent and I can find some different little spots, and appropriately enough, we could take, well, we could take maybe this spot right here at 5 seconds, and we could come down and let's look at this spot right here at around 1 second. And this looks relatively accurate. Again, we're doing a little bit of eyeballing. And so we can now say, all right, well, D2 up at the top there was 125 meters minus D1, which was 0. And we're going to divide that by 5 seconds minus 1. So here I have 125 at this point and 5 seconds, and this would be 0 meters and 1 second. And if I sub these numbers in, I get 125 divided by 4. And in my final line, I will put my units back in. I get 31.3 meters per second. And this, of course, is in the east direction. And there we have it. Our instantaneous velocity at 3 seconds is 3.3 meters per second, 31.3 meters per second east. Again, we want to remember the direction. Okay, so that's one thing. Another way of finding a velocity is by doing an average velocity. Okay, so average velocity is a little bit different. If we come down here, now let's use purple. An average velocity can be found by connecting a straight line from start point to end point and finding the slope. So for example, if I wanted to calculate the average velocity, say over the first 7 seconds of this little life, then I would say, okay, so this train 0 all the way to 7 seconds, and if I connect those 2 points, I then would find the slope of this line, and I could say, okay, V average is equal to D2 minus D1, vector, vector, over T2 minus T1, and a quick calculation then shows, okay, 250 meters east minus 0 over 7 minus 0, and I get 250 divided by 7, and this is going to be again in the east direction, and we get 35.7 meters per second east. And that would be the average velocity of this train over the first 7 seconds. Again, if we wanted to do the average velocity over the first 2 seconds, then you would take a straight line from here to here and connect those and find the slope of that line, and so on and so forth. All right, so there you have it. Here is an example. You want to consider this position time graph that I've shown here. My copy's blacked out because I got the answers. And so this is what I want you to use. Using this model that we just created here, position versus time for a train. So we kind of have just looked at an example. What I want you to do is I want you to try this example for yourself now. Go in and take a look at finding the velocity of the object at 2 seconds, and then find the average velocity over the first 2 seconds and see what you get. So press pause, try this out, and then come back and check your answers with me. Here are, now obviously you've kind of come back and you should have received an instantaneous velocity at 2 seconds that's close to 4 meters per second east, right? Close to it. And you would have had an average velocity that was close to 2 meters per second east. Again, depending on how you draw your tangents and how you draw your lines, there's always going to be a little bit of variation, but you should have numbers that are reasonably close. And if you don't, then ask me about it in class and we'll go from there. Here we have different types of motion, different types of graphs, and maybe you remember this a little bit from, we did something very similar in the last lesson, but here we have all these different types of graphs. So in the first one's done for us. We've got that, yes, indeed, the graph is a curve, which means that since the slope is changing, the slope of this line is changing. It starts off very small down here and ends up very big. The slope is increasing. The velocity is not constant, so the velocity indeed is also changing. Because the graph lies above the x-axis, and its slope is increasing, the velocity of the object is increasing, so it's speeding up, and because it's above the x-axis, it's in a positive or eastward direction. So an example of this would be, say, a bicycle traveling eastward, but eastward in this direction. So if east was down the hill, this bike would be speeding up, traveling eastward. Okay, so bicycle is speeding up in the east direction. This graph, the next one, is a little bit different. It's still a curve, and we know that because it's a curve, that means the slope is changing, velocity will be changing as well. The graph lies below the x-axis, and its slope is increasing. And we can say that because we see where it starts. It starts at almost 0, and it ends down here at a much larger value of slope. And so we can say then, indeed, its slope is increasing. Which means the velocity is increasing. And for something with an increasing velocity, it's speeding up. But this is the important thing next. The reason why this graph is below the axis is because it's speeding up in a negative direction. Or, in our case, westward. So if we were going to draw a diagram of this that was similar, in fact, to the bicycle that we drew here, we could simply draw something that looked like this. Here's our hill, right, in the eastward direction, and so eastward would be up the hill. And now we have our bicycle that looks like this. And so now we're speeding up because here's the bicycle at rest, and of course as it moves down the hill it's going to get faster and faster, but it's not getting faster in the east direction. This way right here, this is the west direction, so it's getting faster in that direction there. All right, so moving along, here we have 2 more examples. This is an object that of course is a curve. Its slope is changing. I put these in here not for repetitiveness, but to prove a point that anytime when it's a curve, we know that the velocity is not constant. This graph lies above the x-axis. Its slope is decreasing. This one, at the beginning, starts out with a pretty high slope and ends with something that's almost 0. So this starts off with a fast velocity and slows down. So the velocity of this object is decreasing, which means slowing down. It's slowing down, though, in a positive direction because it's above the axis, which is eastward. So, an example of this is where we have a bicycle, and here's our hill. This is east, so this is positive. But now we have a bicycle that is going uphill. And of course, because it's going uphill, it is going and will come to a spot where it eventually comes to rest. Because this bicycle, if it just glides and doesn't have someone pedaling, it will just glide up, slow down, slow down, slow down. It's still moving in the east direction, but it's slowing down, and eventually it'll come to stop. All right. The last, you can probably imagine what it is. Again, it's a curve with a changing velocity. Here, the slope starts out big and small. So the slope is, of course, decreasing. Which means the velocity of the object is decreasing. Or, in other words, it's slowing down. But it's slowing down in a negative or westward direction. And of course, I'm sure that you can imagine that what that means for us then is that the bicycle will go uphill, but of course, it's slowing down in this direction, where here's our west, and it just means that the bicycle is still going uphill, so it's slowing down, but it's moving in the opposite direction. And that is a primer on displacement time graphs and how we can find some accelerations and velocities. And next lesson will be all about the velocity time graph.